Okay, we defined the matrix times a vector Ax to be the linear combination of the columns of A using the weights, the entries in X as the weights in that linear combination. So I want to look at another way to view a product. Okay, first, using the definition that we already have come up with, Ax is just going to be using the weights of X in the linear combination of the columns of A. Okay, now simplifying that becomes, just using the scalar multiplication, that's 2x1 minus x1 and 6x1, 3x2, 5x2, negative 2x2, 4x3 minus 3x3, and 8x3. Now, summing the vectors by adding corresponding entries, we get this. Okay, now let's go back to the original matrix. A times X, we had entries of A, I want to get to the product more directly. If you notice, the first entry in the product over here was just taking the entries of the row multiplied by the entries in this vector X, and then adding them together. So we just did 2 times x1 plus 3 times the x2 plus the 4 times the x3. That gave us the entry in that product. Likewise, the second entry in the product was just the second row times the vector x. So negative 1 times the x1 plus the 5 times the x2 minus the 3 times the x3. And the third entry in the product was the linear, it was just a product of entries in the third row with this vector. Okay, now when you look at that, when you take entries in one row like that, or you can think of that as a row vector, and multiply the corresponding entries, I'm going to focus on this first row here. This is called a dot product. When you add the corresponding, you multiply the corresponding entries and then add them together. Okay, so the first entry in the product AX is the sum of the products, called the dot product, of the first row of A and the entries of X. And so then the second row would be the dot product of row 2 of A with the entries in X. And row 3 in the product is the dot product of the third row with the entries of X. Okay, so that's how we're going to look at multiplication. It's a little faster than what we did previously up here, where we're having to take the linear combination of the columns. So let me look at an example that we did previously. We looked at the product 1, 0, 2, negative 5, negative 1, 3 times the vector 4, 3, 7. So now we did that by taking the linear combination of the columns of A with the weights being 4, 3, and 7. So now, using this dot product rule, I'm going to first determine the size. I know that I had a 2 by 3 for A and a 3 by 1, so I'm expecting a 2 by 1 for my answer. So I'm going to have 2 entries with 1 column. The first entry, the first row, is the dot product of row 1 of A with the vector X. So it's 1 times 4 plus 2 times 3 plus negative 1 times 7. 4 plus 6 is 10, minus 7 is 3. The second row will be the dot product of row 2 with the entries of x. So that's 0 times 4 plus negative 5 times 3 plus 3 times 7. So 0, negative 15 plus 21 will be 6. And that's the answer that we got previously when we did it as a linear combination of the columns. So you can also do this as it's called the row vector rule, where you're taking the dot product of rows of A with the vector x. Okay, so if the product AX is defined, then the ith entry in the product is the sum of the products of the corresponding entries from row I of A with the vector x. So that's the row vector rule for computing A times x. Now, just a couple definitions here. The matrix that has ones on the diagonal and zeros elsewhere is called the identity matrix. Now, this is a matrix. It has to be a square matrix. And the diagonal is that the entries in row 1, column 1, row 2, column 2, row 3, column 3, if you're talking about a 3 by 3. So these entries would be the 1, and all these other entries would actually be 0. And that would be your identity matrix that was a 3 by 3. So every different size will have a different identity matrix. So this is an identity matrix that's 3 by 3. The identity matrix that's 2 by 2, and sometimes they denote that as I2. We just have ones here and here with zeros in these other entries. So ones down the main diagonal, zeros everywhere else is called the identity matrix.